Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture, if you recall, we talked about the stress strain relation for the isotropic material, and there we concluded that the normal stress only develop normal strains and shear stresses only develop shear strain, right. And based on that we established the generalized Hooke's law, and based on that we have established the relation between the stress and strain, right. And then we talked about the thermal strain in case of elastic isotropic material, and then we saw that if you have the mechanical strain as well as the temperature strain, then how we can combine these two effect, that means mechanical strain and the combined strain together to get the total strain. Okay. So, now today we are going to discuss about or going to write down the complete equations of elasticity. So, whatever you have learned so far, so we are now writing one by one, so that whenever you are dealing with some elastic say analysis, and if you are recalling the theory of elasticity, then these equations must be satisfied to say that this body or the system is under equilibrium. So, the following equations, so whatever we are going to write, the following equations must be satisfied at each and every point of a non-accelerating. So, that please mind it. So, that should be non-accelerating isotropic linear elastic body subjected to small strain. So, if you consider all these terms, that is non-accelerating isotropic linear elastic and small strain, then the complete set of equations of elasticity can be written as, the first one is for equilibrium, that is for equilibrium condition. Already we have derived that thing for 2D as well as we have extended the same thing for 3D. So, now we can write down that thing for 3D state of stress. Plus x equal to 0 del tau x y del y del x plus del sigma y del y plus del tau y z del z plus y equal to 0, and del tau x z del x plus del tau y z del y plus del sigma z del z plus z equal to 0. Okay. So, these are three equations of equilibrium which must be satisfied at each and every point for a non-accelerating isotropic linear elastic material when you are talking about the equilibrium conditions or the elasticity equations. Okay. So, now what are these capital X, capital Y and capital Z, as we have discussed earlier? These are nothing but the body forces along X, Y and Z directions, right. So, X, Y and Z are the body forces per unit volume. Okay. These are the body forces per unit volume. Okay. Of course, in x, y, z direction, so that you can write in x, y, z direction respectively. Okay. So, these three equations are required for your equilibrium condition. Then you have geometric compatibility. Now, what is that? Already from the name itself, it is clear that you are going to satisfy some compatible condition, right. So, you have seen that if you apply stress, okay, some strain or the deformation is happening, but this deformation, okay, cannot be arbitrary. It should follow some rules. Okay, there is some rule of the game, and that rule should be followed by this deformation. That means, if I consider say a kind of say body, okay, and I am applying externally applied forces all round. Okay. Now, if I consider 2 points here, okay. Now, after deformation, this point may move little bit, say it is coming here, and this point may move little bit and it is coming here, say. So, I can use different colors, that will be convenient for you to understand. So, after deformation, this point is moving here and this point is moving here, but nowhere this say point, I mean point means some say particle. Okay. So, we are considering two particles, and now after deformation this particle is going to this location and this particle is going to this location. Now, nowhere this particle should cross over, right, should overlap the previous particle. So, that is a kind of compatible condition. Okay. And similarly, you should not get the development of crack inside the system. Suppose if this is the body, you are applying some force, your body is a continuum body, right. Even after deformation, that will be remaining continuum. So, you will not be getting any discrete gap in between the system or the body. Okay. So, these are the things which can be satisfied by the geometric compatibility. Okay. So, the geometric compatibility is, or can be written as, in terms of the strain and the displacement, okay, as already you have seen, already you have derived that epsilon x is del u by del x, epsilon y is del v del y, and epsilon z is del w del z, and similarly gamma x y equal to del v del x plus del u del y, gamma y z equal to del w del y plus del v del z, and gamma z x is equal to del u del z plus del w del x. Okay. Where your u, v and w are the velocity or the displacement components, right. They are nothing but the, if it is time dependent, then displacement, I mean velocity, or otherwise displacement anyway. So, that is u, v and w are the displacement components along x, y and z directions. Already we have derived that thing. We are not now writing down all those things, okay, systematically, and at the same time we are defining those equations, okay, as per their function, right. Previously we have defined the equilibrium equations. So, that is required for satisfying the equilibrium condition, and this set of equation is required to get or to satisfy the geometric compatibility, and next set is nothing but your stress strain temperature relations. Okay. So, all those equations we have derived, so now we are writing down one by one systematically, where epsilon x can be written as, in the previous class we have discussed that, sigma x minus nu sigma y plus sigma z plus alpha, coefficient of thermal expansion, into T minus T naught, that is the difference in temperature. Okay. Similarly, epsilon y is equal to 1 by E sigma y minus nu is nothing but the Poisson ratio, sigma x plus sigma z plus alpha T minus T naught. Okay. Similarly, epsilon z is equal to 1 by E sigma z minus nu into sigma x plus sigma y plus alpha into T minus T naught. Okay. And your gamma xy, similarly gamma xy can be written as tau xy by g, that is g is nothing but the shear modulus, and gamma yz can be written as tau yz by g, and gamma zx is equal to tau zx by g, right. So, these three or rather 6 equations are nothing but the stress strain temperature relations. So, this is basically the complete equations of elasticity. So, if you are dealing with theory of elasticity for whatever type of system I told, that is non accelerating, isotropic, linear elastic, and of course, small strain if you are considering, then these equations, okay, must be satisfied, okay, and these equations will be required to get the complete information about the system. Okay. Now, we are going to discuss about the criteria for initial yielding. So, criteria for initial yielding. So, there sometimes this is also known as your failure criteria or whatever. In different books you will see failure criteria or criteria for initial yielding or say yield criteria. Okay. So, different names have been proposed in different books. However, so this is the criteria by which you can say that if you apply I mean say if any system, okay, is under different externally applied loads or the forces, then basically at which point the material will start yielding, okay, that kind of information is very much required for the design engineer. Okay. So, for that particular purpose you should know for any particular material, or say if it is 1D or 2D or 3D, it does not matter, but the thing is that whatever material you are considering or whatever system you are considering, you are applying some externally applied loads, and under that circumstances whether the material will yield or not. And you know by this time that yield point is a very, very important say point. So, this point is basically I mean making the demarcation between the elastic limit or the elastic say behavior and the plastic behavior, right. From the yield point basically your plastic deformation initiates. So, that point is very, very important to be determined. Otherwise, what will happen, say suppose you are going on increasing the load on the material or the body, at some point you will see that the plastic deformation starts, and without taking any extra load the whole material starts collapsing suddenly, right. So, because as you have seen that when if you are talking about the perfect plastic condition, then you have seen that after reaching the yield point there is no increase in the stress, rather the strain will be going on increasing. So, to avoid those kind of situations in the real life, we should know that at which point or at what kind of combination of loads or the stress the material will start yielding, right. So, if you consider 1D condition, so yield criteria will be dependent only one directional or 1D state of stress. If you consider 2 dimensional state of stress, then basically 2 stress directions will be making this yield criteria. If you consider the 3 dimensional state of stress, then all the stress components. So, it is a, what I mean to say that it is a combination of stress which will govern the yield initiation of yielding, right. So, the first theory, the first criteria says, what does it say? Because we are now defining some rules, and the material, it is not required that all the materials will be following this criteria. So, we will be defining 2 criteria basically. This is the first criteria and we will be defining the second criteria. Now, it is not necessary that all the materials, whatever you are seeing in the universe, that all the materials will be say following this first criteria, right. Some material will follow the first criteria, some material will follow the second criteria, and depending on that basically failure theory have been developed in the plasticity. Okay. So, now we are defining the rules or the criteria. Now, we are not talking about the which material is following this. So, that depends on the material behavior, that we are not talking about, but we are defining the rules or the guidelines. Okay. The first criteria says it assumes that yielding can occur in a 3D state of stress when the root mean square of the differences between the principal stresses reaches the same value which it has when yielding occurs in the tensile test. Now, what does it mean? So, this is the criteria, this is the definition of the first criteria. Okay. So, first criteria says that it assumes that yielding of a material can occur in a 3D state of stress when the material or when the system is under 3D state of stress. Okay. When the root mean square of the differences between the principal stresses, root mean square of the differences between the principal stresses reaches the same value which it has when yielding occurs in the tensile test. Now, what does it mean physically? Okay. So, let's see that thing physically. Okay. Now, let y be the stress at which yielding begins in simple tensile test. Okay. So, we are just defining let y, I mean I do not know that will be different for different material. If you use steel, y will be different, if you use copper, it will be different. For different material, different say metal or different material, whatever you are considering. Okay. So, for that y is the yield stress, okay, for simple tensile test. So, what does it mean? What is simple tensile test? As I think you might have done that thing in your undergraduate, some simple tensile test of the steel rod or the aluminum rod or whatever. So, why is that yield stress? Now, simple tensile test, what we do generally in the lab, we are taking a rod or 1D or one dimensional say member of a particular material, okay, and we are applying tensile stress. So, if my coordinate system is like this, okay, and say that is we are just mapping that thing 1 2 3 coordinate system. Okay. 1 2 3 coordinate system means principal stress. We are just saying that maybe XYZ coordinate system, actually it is XYZ coordinate, that is the general state of a coordinate system, but however we are just mapping that thing in 1 2 3 coordinate system, which are the principal axis say, and where one axis is matching with x axis, 2 axis is matching with y axis, and so on. For the time being, we are just assuming that thing. Okay. It is not necessary that all the times one axis will be matching or following the same direction of x axis, not necessary. Already we have seen that thing in different numerical problems as well as whatever we have discussed. Anyway, so this is the 1D say 1D tensile test we are doing, we are performing on some material. So, we are applying only one directional stress, okay, that is sigma x along x direction. So, in this case, if we say, and we are what we are observing on this plane, this is my x plane, this is my positive x plane, this is my negative x plane, whatever from your definition you know. Now, on the x plane basically you have only the normal stress acting. So, therefore, it is eventually the one of the principal planes, yes or no, right, because there is no shear stress acting on that particular plane. So, x plane is virtually becoming one of the principal planes, and that is nothing but your major principal plane, yes or no, that will be your major principal strain, and x axis is virtually becoming major principal axis, that is shown here as 1, right. Similarly, if you see the y direction, so this plane is a y plane, okay, this plane is positive y plane, this plane is negative y plane, and the y plane basically you do not have any stresses. So, if you do not have any stresses, and therefore, of course, you do not have the shear stress. So, if shear stress is 0 on a particular plane, so that plane must be one of the principal planes, is not it. So, that you have got. So, y plane is also another principal plane, and that is defined by say axis, and the y direction is becoming one of the principal axis, and that is say axis 2 and so on. And z plane is also, because we are only applying unidirectional say tensile force, right. So, z plane and y plane are completely free from any stress. So, they have to be the principal planes, and y and z axis have to be principal axis. Okay. So, sigma x is nothing but your major principal stress, from the discussion we are getting it, is nothing but say y, because we are continuously applying the tensile force, that is sigma x, we are going on increasing and we are observing the strain happening, and at certain point you will be observing the, if you plot the stress strain curve, at certain point you will be observing the yielding initiates, right. At that point, that is the maximum, say sigma x is possible, okay, which is possible at the point where yielding starts, is not it, okay. So that is nothing but, by our definition, that is nothing but y, okay. Now what about other principal stresses, sigma 2 and sigma 3, because sigma x is nothing but sigma 1, but sigma y and sigma z are 0. So therefore they must be 0. Understood the logic and the discussion whatever has happened here, okay. So we have got sigma 1, sigma 2 and sigma 3 for a uniaxial tensile test, right, okay. And in that case basically sigma x, sigma y, sigma z both all are principal stresses virtually, because there is no shear stress on the planes, okay. So now, so as per the criteria, what does it say? That it says that the state of stress, the 3-dimensional state of stress, when the root mean square of the differences between the principal stresses reaches the same value which it has when yielding occurs in the tensile test. That is the first, that is the criteria actually. So we are now defining the, so therefore in the tensile test yielding occurs root mean square of the differences of the principal stresses, 1/3, this is nothing but your root mean square of the differences of the principal stresses, right, sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. This is your root mean square of the differences of the principal stresses, okay. For your uniaxial or the simple tensile test, that will be becoming as 1/3 sigma 1. What is the value of sigma 1? Simply y. So y minus 0 whole square plus 0 minus 0 whole square plus 0 minus y whole square. So from there we can get root over 2 by 3 y, okay. So we can simply write root over half sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square equal to y. So this we are getting from our first criteria, that means for initial yielding or the first, this is my first yield criteria. So what you are getting here, so what basically the interpretation coming from this equation, that means if you have the body or if you consider any body, okay, under the action of sigma 1, sigma 2, sigma 3, these are the principal stresses say, okay. So 3-dimensional state of stress. So under the action of sigma 1, sigma 2, sigma 3, now for the combination of sigma 1, sigma 2, sigma 3 which will satisfy this condition, okay. So that condition or that situation will cause the yielding, okay. For the combination of sigma 1, sigma 2, sigma 3, if you arrive to this situation, okay, where this left hand side is becoming equal to y. What is y? Y is nothing but your your that is the stress at which your yielding starts, okay, in case of simple tensile test. So, you perform, so whatever material you are considering in 3-dimensional state of stress, you just consider the or you just perform the simple tensile test on the same material, you find out y from the laboratory, okay, and then that y should be equal to the combination of sigma 1, sigma 2, sigma 3 in such a way that it should satisfy this equation. So, up to that point basically, I mean once you reach that condition or reach that situation, then yielding will initiate for that particular material, okay, because that is coming from the first criteria, and this is known as in mechanics, this is known as Mises, simply Mises or say von Mises. Von Mises yield criteria. Okay. So, this is popularly known in mechanics as von Mises yield criterion. So, you have got now what is von Mises yield criterion, right. This you will be getting from your laboratory experiment. Once you get that, then for any combination of sigma 1, sigma 2, sigma 3, if it is satisfying this equation, then that will cause yielding in that particular material. Okay. So, I will stop here today. In the next lecture, we will be continuing with the second yield criteria, and then we will be discussing something about engineering strain and true strain, engineering stress, true stress, engineering strain, true strain, and that is all. Okay. So, thank you very much. I will stop here today.